everyone, I am Asagatikari. So today I am going to talk about the work which I have submitted to IMRC 2025. The title is Synthesis of TiO2 Nanostructure Using the Mechanochemical Process for Investigating their CO gas sensing characteristics. Starting from the introduction, TiO2 presents fascinating optical, electronic, structural, magnetic, and electrochemical properties which we have received considerable attention from both the scientific and technological communities. TiO2 is an n-type semiconductor with a band gap greater than 3 electron volt, existing in three phases: brookite, anatase, and rutile. Based on above mentioned characteristics, the TiO2 is suitable in diverse applications such as photocatalysis, photovoltaic, voltage, electro and thermochromic windows, sensors, optical switching, memory devices, etc. The growth technique can also impact the quality of the materials depending on their nature and applications. A ball milling is a typical machine that produces a strong mechanical force to alter the material's properties. This investigation initially focused on the synthesis of TiO2 powders at different milling times, while the milling speed kept constant. Afterward, the material properties of TiO2 powders, such as structural, morphology, composition, and optical properties, were thoroughly studied. Finally, these TiO2 powders were employed to detect the carbon monoxide gas sensing applications. And next, we have here the experimental details. We have the equipment where we have done milling process in different times: 0, 2.5, 5, 10, 7.5, and 10 hours. And also we have characterized by different techniques: structural, morphological, optical, and gas sensing application and textural properties, which later I will discuss. From results and discussions, we have here the grains. Like initially, it is geometrical size, very larger, more than 1 micrometer, and after that, it is after the 2.5 hours of milling, it decreases slightly, but there is still some larger grains available. After completed 10 hours, we have seen homogeneous grains in less than ranges is around 100 nanometer grains, and is very homogeneous. You can see from the figure E. And after that, also we have checked the composition of oxygen and titanium in the film, and we have got the uniform distribution of the atoms. And as we can see from the peaks, obtained peaks of titanium and oxygen, can come from the oxygen and titanium samples, and also their compositions, which is like oxygen content is slightly decreased. And after that, we have also checked the TEM to verify the results obtained from the same, that the particles we have obtained is nanoparticles or not. So initially we have done zero without milling, and after milling of 10 hours. So initially it is confirmed that is the geometrical size and very large grains obtained, and after that, after the milling, we can see the very small, less than 100 nanometer grains can be seen, which is also support the same results. And from the results of interplanar distances, it confirms the tetragonal phases, which will describe, which is support from the excited results, which we have obtained from the excited results, that the peaks, the 1 and 0, which is preferential for, in this case, is confirm the tetragonal phase of the TiO2, and it is rutile phase, we can say. And after the milling times, the crystal size or crystallinity, you can see, is decreasing, since the ball milling process can decrease the size, particle size can, so it can also confirm that with an increase in ball milling, the crystal size is decreases. Then after we have checked the band gap in order to see what is the optical property you can vary from the reflectance data, and we use Kugelka-Munch plots to calculate the band gap. We have with increasing band gap, with increasing milling times, the band gap varies from 2.80 to 3.22 electron volt, and 3.2 is the normal band gap of the TiO2. And this information can verify that the band gap is near to the normal band gap of the TiO2. Then we have checked the textural properties, and we have like normally in sensing property, what effect is bed area bed area. So bed area can generate the more active sites, so it can generate more with more active site can decrease the can increase the conductivity and consequently sensitivity of the samples. So here we have what we have is with increasing in milling times, but normally we have done is zero without milling and after milling of 10 hours, and after milling the bed area is drastically improved. You can see also from graph, and also the pore size is less than 50 nanometer, is correspond to the more mesoporous particles. And finally, we have worked on the sensitivity static mode, and we have checked on different for the samples without milling and after milling for with at different operating temperatures 100 to 300 degrees Celsius, and different gas concentration of from 0 to 500 ppm. So with this we can see the variation. We can initially it is very high for all the conditions, and with increasing concentration the, the, the resistance decreases, and we have calculated with the distance with initially it is with air, and after that it is concentration of the CO gas. So we have obtained that with a increasing temperature the sensitivity increases for both cases, but with the bone meal samples the sensitivity is higher, more very far higher than compared to the zero samples without milling. From this result, we can conclude that the results obtained from XRD and Raman spectroscopy were compatible with the tetragonal crystal structure of TiO2, having the crystal size of the same sample in the range of 20 and 36 nanometer. The bandgap values for TiO2 was enhanced from 2.8 electron volt without ball milling to higher values up to 3.22 electron volt for ball mill samples, which was calculated from Kubel-Kammong theory. The large and geometrical shaped grains for TiO2 before using the ball milling were converted into nanoparticles with irregular shapes and size of grains for ball mill samples. The presence of oxygen and titanium elements were confirmed from EDS spectra. 10 micrographs were also compatible with the same results, and the observed interplanetary spacing from the 10 results were aggregable to the XR results. Bed analysis observed the larger bed area for samples and with the mesoporous particles for both cases. The CO gas sensing response was enhanced with an increasing operating temperature and gas concentration, comparatively higher sensing response noticed for the ballooning samples. So we would like to acknowledge the people who are involved in people from Simbesav, and in Histophysica, and there are some references and contact my contact if you have any questions. Thank you very much for your consideration.